Hello everyone, this is Ming. In this video, we are going to go through the details for Big Data Cloud Platform using Spark. First, a very brief introduction on the Big Data Cloud Platform and the history. So as a statistician, we're all familiar with data. We're dealing with data on a daily basis. But the size of the data has been increased from a kilobytes to terabytes, now even to petabytes of data. So the size of the data has increased dramatically in the past 20 years. And the size of the data actually is much more than the typical capacity of a one computer, laptop, desktop, or even the most powerful desktop. The memories cannot fit all the data in. So that is kind of a reality in today's world. Basically, data is beyond the capacity of one single computer. But oftentimes, people want to use all the data to make decisions. And let's look at the history of statistician in the America. So created in 1839, the second oldest continuous operating professional society in the US. In old times, data is usually in a piece of paper, in a table that is fairly small in size. In 1934, the data, the first actually statistical laboratory in the US university is created. At that time, data is in tapes and punch cards and tables. Around 2000, data in one computer's disk or memory. That's actually data is getting larger and larger. The speed is faster, increased very quickly. So even the most powerful computer cannot hold all the data in the memory. But unfortunately, most of the software system that statisticians are familiar require the data to be in the memory to process. That's limit a lot of potential applications. And now data is basically so large, it has to use the cloud infrastructure in the big data system to store, process the data, and retrieve the data and feeding models on top of that. So the difference between a single computer and cloud computing is for a single computer, we all know it has three major components: CPU, memory, and disk. So that's a three very basic component. For cluster of computers, each element has a three. Each unit had the same component. They're all connected together. But the ultimate goal for the cluster of computers is basically their shared disk. All the disks can be considered as one huge disk. Shared memory, all the memories across different kind of units can be waived as one huge memory. And because there are CPUs and memories for each unit, we want a parallel computing of all the CPUs for model feeding and data process. It's basically shared memory, shared disk, and parallel computing is scalable. So if we need more, we can add more nodes and add more units. So depending on the application, the scalability can be large or small, depending on the usage. But historically, this cluster of computers, the software developers is actually make it accessible. So because each unit has each node has its own CPU, memory, and disk, so there has to be algorithm to developed to make the data redundancy. Basically, once one node is getting knocked out, so the data can still be recovered. The computation can still continue. So that's basically scalability to process large data sets, robust and reliable for data safety. And maintenance of computer clusters usually is very tedious, needed dedicated resources. And in the cloud environment, the users are more focused on application and left the professional software developers to maintain in the cluster. So in the early days, it is the Hadoop system using MapReduce for distributed storage and process of data. And it has a Hadoop distributed file system. So basically, the cluster is using the computing hardware that is called commodity hardware. That's pretty much the same thing that you and we used in our the desktop hardwares. So as you can see, once you have like 100,000 units of those CPU, memory, and hard disk connect together, you have a system, and the reliability of the system from a hardware point of view is pretty low. So there are always hardware failures, like hard disk failed, memory failure, or CPU is burned out. So it happens all the time in a data center. So we have to kind of like the software developer has to develop a robust algorithm such that the data are actually reproduced in a few different kind of nodes, so such that one node get knocked out, it can be replaced, and the data still remain the integrity. No data will be lost. And the computation is also need to consider the distributed and parallel computing for the distribution. So the Hadoop distributed file system is basically ensure the system, each individual node can fail, but the whole system remains healthy, and the users do not need to worry about the background. The MapReduce is basically one way we kind of divide and conquer for the computation and data processing. In early days for Hadoop, there's two applications on top of that, Hive and Peak. Those are applications for easy access to the data stored in the HDFS system and do some applied analytics. But nowadays, then those applications are rarely used because for day-to-day analytical work, a new system has been developed on top of that. It's called Spark. So it's built on top of the HDFS system on another cluster file system. Is provided in-memory computation for a much faster speed. So we are consider all the data stored in the memory across all the CPUs. So it's provided parallel algorithm for many machine learning algorithms methods through the library. It also provided easy-to-use interface for data scientists, especially for statisticians. Now we can actually using R to drive Spark jobs in the Spark system. So now in the modern cloud environment, we do not need to know too much about the background, and we can actually use our familiar software like R with correct setup and connections to drive all the Spark related computation. So basically the bar for statistician to access Spark for big data analytics has been dramatically reduced. Now, hopefully after this section in the hands-on part, you will be able to write your own R functions to drive Spark cluster for data pre-processing and feed some typical machine learning models. Cloud environmental providers, there's quite a few, like Amazon's AWS, Microsoft Azure, and Google's cloud environment. So those are actually provided heavy-duty enterprise-level applications. For our training purpose, I prefer to use the Databricks Community Edition, which, as you already know, it is straightforward to use, and then it is free. And the backend for Databricks Community Edition is AWS or Azure Cloud Environment. So for beginners, the Databricks provide an easy-to-use system, and using the notebooks, we can actually run R, Python, Scala, or SQL scripts very easily. So now let's focus on the Spark through the Databricks system. As I mentioned earlier, we are going to using R notebook because for statisticians, we are all familiar with R. And one of the required library is the Sparkly R package, which enables connection between the master, or what we call a local node for the notebook, to the Spark cluster environment. It's going to install a lot of dependencies. It may take a little while to finish, so be patient in the hands-on part of installing those libraries. Once the library has been installed, what we need to do is actually to create a Spark connection. The Spark connection is going to link the local R notebook environment to the Spark environment. The local R environment probably is running on a particular node, and it has its own memory, CPU, and hard disk. For the Spark environment, we can consider it is a separate system with 100 or even 1,000 computation node with a collection distributed data across different nodes, and computation will be parallel as well. So to help us understand the connection, because the Spark connect, after we call this function, we exactly return a local R object. This local R object SC is more or less create a bridge or tunnel between the R local notebook to the Spark environment. So basically, using the Spark connection, we can create a bridge between the Spark data frame to one of the R local object that I'm going to show in the next page. So basically, we are going to call some functions in the R local notebook to a particular R local object, but the operation is actually add the Spark environment to a Spark data frame. So basically, we're using the R notebook to drive the computation in the Spark cluster using the Spark connection HC. After we establish the connection, we need to copy a data set to Spark cluster. So for a brand new Spark cluster, there's no data frame at all. There's no Spark data frame. What we can do is actually copy, for example, the ARIS dataset, which we are all familiar, is a very small dataset. For illustration purpose, we're going to copy the ARIS dataset from the local R notebooks computing environment to the Spark cluster using SDF underscore copy underscore to with the Spark connection SC we just created. X here is what kind of data set we want to copy to the Spark system, and it is the ARIS dataset. And after we call this function, it's return a local R object, ARIS underscore TBL. So this is the local R object that we are actually created. It is basically a pointer to or handle to the Spark data frame ARIS. So in the future, whenever we are going to apply functions to ARIS underscore TBL, please keep in mind the computation is actually for the ARIS data frame in the Spark cluster. Um, so this address underscore TBL is just a representation of the Spark data frame in the Spark cluster. In most cases, in your real application, your data is already in the Spark data frame. In such cases, what we need to do is simply create a connection between the our local object to the Spark data frame by using the TBL function. So the basically my underscore df is the Spark data frame in Spark cluster, and my underscore df underscore TBL is going to be the our local object. All right, now we understand that Aris underscore TBL is a R local object, but it is representing the Aris Spark data frame in the Spark environment. So the good news is with Sparkly R library, we can use nearly all the functions in dplyr to the Spark data frame directly by apply that to Aris underscore TBL. Like for example, we can use the mutate function, group by function, summarize function to the Aris underscore TBL function and Aris underscore TBL object, which is just a small R local object, but all those computations actually applied to the Aris and Aris Spark data frame using Spark's parallel computing. So for this small data set, we do not see any significant improvement. But let's suppose you have a data set, Spark data frame that is a few dozens or few hundred gigabytes in memory in size, and you want to do all those kind of pre-processing, and then using Spark is going to be much faster. And sometimes, in most cases, when the size of the file is so large, and we cannot even do it in the local R object in the local R computing environment. Once we finish our pre-processing and in most cases data aggregation, we have to collect the result back for downstream analysis. Even though we can run many of the dplyr functions in the Spark data frame, but we cannot apply functions from other packages, other libraries to the Spark data frame directly. To do that, we have to collect the aggregated data back or subset of the data back to the local computing environment. And once it's collected back using the collect function, now it's become a local R data frame, the Aris underscore summary. And then we can apply any functions from any libraries to Aris underscore summary, just as it's your local R environment. But one of the biggest advantage in Spark is there are already many popular statistical and machine learning models developed in the Spark system. It is all leveraging the scalable parallel computing and distributed data, but that's the power of the Spark cluster. Those models like linear regression, logistic regression, random forest, and k-mean clustering, those are the very typical machine learning and statistical learning algorithms, and those are all implemented in Spark environment. Very conveniently, we can use our notebook to call functions to apply this machine learning algorithm to Spark data frame with minimum effort for statistician to leverage the Spark environment. We do not need to learn, like for example, Scala. We do not need to learn Hadoop. All those are not required. Everything can be done using the R notebook in the R environment. Like for example, if we want to feed a linear regression model to the Aris dataset, what we can do is actually by calling the ML underscore linear underscore regression from the Sparkly R library. X is basically the local R object that is referring to the data frame, the Spark data frame, and we define what is the response variable and what are the features for linear regression. And once it is fitted, we can look at the summary. of the fitted result. We can also feed a k-mean clustering algorithm to a Spark data frame by calling ml_k-means function. And in this function is basically k is the number of clusters, features is basically all the features we want to use in that Spark cluster to feed the k-mean algorithm. And once we feed a k-mean algorithm, the k-mean model, we can actually collect the predicted value for each row of the data, and then once we collect them back, the prediction is become a local variable, and we can apply any downstream analysis using any functions from any library. So as you can see, it is fairly easy, straightforward to use R and Sparkly R library to apply any of the dplyr functions to a Spark data frame and fit typical statistical and machine learning models for a Spark data frame using our notebook.